All right, hello everybody. All right, we're gonna get started. Welcome to our final plenary session of the day. It's gonna be Professor Katerina Fragkiadaki from Carnegie Mellon University. Katerina Fragkiadaki is a JP Morgan Chase Associate Professor of Computer Science in the Machine Learning Department at Carnegie Mellon. She got her PhD at UPenn, University of Pennsylvania with Jian Boshi, and after 3 happy years at UC Berkeley, as a postdoc with Jitendra Malik, she is now doing great work, amazing work at the faculty level, and really, you know, I am so thrilled to have her here. If you ask all the students in my group who they love the most, whose work they follow, it's Katerina, and so I'm grateful that she can share some of her latest results and her amazing accomplishments with you today. Thank you very much. Let's give her a round of applause.
Thank you, Chad, for the kind introduction. Thank you, everyone, for being here. It's a great honor, a great pleasure. Thank you for inviting me. So I will discuss a little bit the work we do in my group on embodied agents and to enable to see, simulate, and reason and plan. I'll start from Kenneth Craig, a young philosopher. He died really young in a bicycle accident back in 1940s. But before that, he published a book where he says that he was the first to essentially put forward the idea of a world simulator, that an embodied organism, if he has access to a world model, that it can query for different actions to see the consequences, to run counterfactuals in his head, then this will make it more intelligent. So essentially, what Kenneth is suggesting back in 1940s is to learn predictive models of the world and then choose actions by looking ahead within that model, that mental model, okay? And these predictive models of the world, those simulators, up till today, it's an open area of research, what exactly form they should have, what representations they should be representing. One suggestion is to look ahead and, you know, generate the future in pixel space, on observation space, in observation space. And you see here results of Sora, Sora 2, and other video generative models, extremely impressive and getting better by the day. And those models, essentially, they take a history of video frames and they reason at the token level, where the token is just a feature of a special temporal patch for the video they're going to generate. Okay, so we generate the future. What if we just imagine the future in pixel space? And then there's another way to generate videos here using a physics engine. And a physics engine essentially is a code that humans write that controls how different entities move, collide, and react to forces. And the entities, the tokens in a physics engine, are not patch features like in video models, but rather they're object meshes and part meshes and particles. And, you know, the physics solvers essentially command the motion of those particles and meshes as what you see here. And then there is a camera that renders the scene and gives us the final images. And it has been advocated from human vision researchers that the human brain does something more like the second as opposed to the first, the video generative paradigm. Right? We take a scene as input, take 2D images as input, but in our head, we try to recreate some form, approximate, an intuitive form of the 3D reality, predict the future in terms of motion of where things are going to go, not directly appearance, and then reason in that space. So in this talk, inspired by that, I'll discuss three themes. The first is how can we take foundation models, visual language models, VLAs, and inject to them more geometry and physics-inspired representations to make them generalize better, essentially some inductive bias from geometry and physics. The second is how can we use machine learning, essentially computer vision and generative models, to automate robot data creation within a physics engine. And the last part is about test-time thinking for robotics. How can we revisit robot planning from the perspective of generative models? What can we do better than the traditional model predictive control paradigm there? So let's start from inductive biases and VLMs. Okay, how can we, I mean, we heard earlier from the panel, but also from multiple talks in the conference that we need our agents and foundation models to be more spatially intelligent. So let's see, GPT-4 and other foundation models, the way they work is they take a text stream, they encode the text into text features, they take an image and they encode it also in visual tokens, and then they predict answers. And the problem with this paradigm is that once you apply it for embodied agents, that actually the input is a continuous video, okay? You try to tokenize now this video input, and the result is that you have too many tokens, too many patch features that feed into the VLM, and very quickly they can overflow the context window, okay? And they're quite redundant also, right? So we have this, so this makes VLMs and VLAs extremely expensive and wasteful, because they need to reason and have quadratic, essentially, attentions between visual tokens that are very similar. So I come from 3D computer vision. That's how I started, essentially, in my faculty career. And, 3D computer vision it's a field that was developed very, separately from all these foundation models and large pre-trained models and so on. And what we said is, what if this is not the case? What if we can take the paradigm of visual language models and just change the positional encoding in the transformer? So VLM is a sequence model, and when you have a sequence model, you need to know where each token is coming from. And for this reason, the transformer has what's called the positional encoding that encodes every token, the XY image location, as well as frame index, like 1, 2, 3, and so on, where this patch feature is coming from. And what we said is we can make our VLMs spatially intelligent, like to understand space much better, if we just, instead of encoding in this positional information, the pixel coordinate and the time, instead we encode 3D world coordinates, okay, that are given, for example, by a SLAM system, simultaneous localization and mapping, which is, one of the oldest themes in computer vision back in 1980s. Actually, a lot of breakthroughs, and they keep getting better, and learning has helped SLAM systems be more accurate and so on. So basically, you can see the visual tokens in videos in two ways: as patches that sit on images, or as 3D tokens that are sitting on the world scene. And you can change the positional encodings accordingly. So we have a series of papers that essentially look into this idea. The recent one comes from ICML 25. We call it UniVGL because it unifies 2D and 3D perception into one model, in which, in 3D, the positional encodings encode XYZ coordinates, and attention, 3D relative attentions in that space fuse information across images. In 2D, positional encodings encode information within the image, the pixel coordinates, so you fuse information within a single image, and then you can interleave those two layers, or use now we can use essentially the 2D foundation models and just inject 3D awareness. And the reason we want to do that, and we don't want to start from scratch, is because we have massive pre-training that we can exploit in this way. So the architecture looks like this, exactly what we saw earlier. The video comes in, but then the tokens are assigned those XYZ positions, and you can also massively compress the tokens by merging tokens coming from the same XYZ location of the scene. So UniVLG essentially can take any video and any image, so it can consume both RGB images as well as post RGBD video sequences and detect objects, ground referentials, answer questions, and so on. And the result is that with a much smaller model, massively smaller model, you do better than GPT-4o on answering questions on those long videos that embodied agents would see, okay, thanks to this compression that happens with the 3D information. So we see that 3D deductive bias and VLMs help us tremendously to essentially, shrink the context length of the visual tokenization. So let's see what they can do in visual language action models. So we see VLAs, a lot of previous talks mentioned them, so I'm not going to go into details, but most of the VLA papers that come out, they have the same architecture, which is we have a text instruction, and then we have a video from the robot, like that essentially captures the different images that the robot is seeing at a specific time step. And then these tokens, text and visual, they feed into an action decoder that predicts action sequences, action chunks, through a denoising objective. And this denoising is actually very useful because diffusion models can capture multimodality in learning from demonstrations that regression would not be able to capture. So we call those diffusion policies, right? So they have these diffusion heads or flow matching heads. So the idea here with the 3D inductive biases is as follows. We know that the robot will act in the 3D world, will have to move its end effectors in the 3D scene. So what if we encode those visual tokens that the robot sees from its camera in the same 3D space as the action tokens, which are going to decode the robot actions, okay? And the way we're going to do that is we're going to use robot calibration. We assume that the robot knows the transformation between the robot frame, where its end effector actions are predicted, and the camera frame, where it's the input. And if you don't know it and it's hard to compute it, you can learn it from the data as the data stream, the video stream of images comes to the robot. I mean, this is a very basic task, let's say. So if you have this calibration, you can do this thing that I will discuss, we call 3D visual language action models. Now, there are a lot of 3D VLAs out there, but this specific one essentially has excellent results because of this co-embedding of action and visual tokens in the same 3D space. So we have a robot, it can have one camera, or it can have head camera and wrist cameras and so on, and it takes pictures and tokenizes those images, right? And then lifts those tokens in 3D by using depth, okay, for example. And then you can aggregate those visual tokens if you have more than one camera. And then what you're going to do is you're going to denoise a sequence of action tokens. And for every action token, will predict essentially the end effector in a future time step. This is what an action token is going to do. Okay, this is going to generate trajectories of future actions, how the end effector of the robot should move. And so we'll embed those action tokens and visual tokens in the same 3D space, and the information fusion between them will be through 3D relative attentions. So these are attention layers that the absolute XYZ information never shows up because you want to be translation invariant. So in these relative attentions, and then it's a major evolution after transformers, the relative transformers, essentially these attention operations only depend on the relative arrangement between two tokens. So let's see how this model is going to work. And of course, you have also as input the text instruction, what the robot is supposed to be doing, and the history, the proprioception history. And you fuse this information through attentions, and then you iteratively denoise. So here are 60 samples now that I'm showing from the model that are all concentrated among some very few modes, okay? And of course, it's a sampler because it's a diffusion model. And you can be predicting trajectories, or you can be predicting key poses. And this is the task of putting grapes in a bowl. So these VLAs that I'm discussing are all trained from demonstrations. And the reason that you see that all these 60 samples concentrate in those three modes is because one demonstration first picked up the green grape, the other picked up the red grape, and the other the black grape. And you see that the generative model here, our policy, captures these three modes very accurately without hallucinating extra modes and so on. So we call this model 3 diffuser actor, and is at the top of the benchmarks across multiple, let's say, simulation benchmarks that are available, because only in simulation you can do apples-to-apples comparisons with other models. And we have a follow-up, very recently archived, that we extend the same model for bimanual manipulation in a very obvious way. You just need to denoise now 2 sets of action tokens, one for every end effector, okay? And we compare, again, on bimanual benchmarks against, top performing alternatives. And you see that our method, 3DFA, is the top, the red, and the 2D version is the second best. Okay, and we have also here pi0, which we had to adapt to predict key poses to make it more complex as opposed to, robot joint angle trajectories. And so this is in simulation. And in the real world, again, we consider a bunch of tasks. I'm going to show you. We collected 40 demonstrations using the mobile Aloha platform. And then we trained the models. And again, this 3D VLA that exploits these 3D inductive biases coming from calibration of embedding visual and action tokens in the same space does much better. Now, unfortunately, whatever I showed is trained from demonstrations, and an earlier talk also mentioned that, okay, how can we train our robots? Where will the data come from, right? So big companies and rich startups do invest a lot on scaling up demonstration collection, okay? So if you think about it, humans never learn in this way. We never teleoperate other humans. Our parents never take over our hands and try to get us to complete a task, very rarely. They need to be really frustrated to do that. But right now, this teleoperation is the dominant way that we collect training data for robots, okay? Now, unfortunately, in an academic lab, this is impossible. It's a waste of resources. Moreover, knowing from self-driving companies, each one collects its own data, they never share. We don't expect these robot demonstrations, teleoperate demonstrations, to be shared ever, okay? Because they cost a lot of money, so why would anybody share those? So can we find another way of scaling up robot data, all right? So this is now my next bullet. So here, let's see what has happened in robot locomotion. This is an impressive video. I really love it. You see all these nice skills that this quadruped is doing, balancing on two legs. Now it's going on the flat terrain. Now it's going on the hill, and so on. It's going to go now the mountain, slope. Of somebody tells it the direction, and then it figures the rest out on its own. So how this robot was trained? Well, clearly not from, this is not trained from teleoperation. It's not trained from demonstrations. It's just trained from experience, massive reinforcement learning in simulation. That's number one. Number two, the terrains have nothing to do with mountain slopes and gravel and deformable sand and so on. This is just rigid scenes. When the robot walks on them, the terrain doesn't move, okay? The terrain is static. And this simulation is very, very, very fast. And this brought a revolution for robot locomotion. The same way that GPUs brought revolution on neural network training and deployment in 2012, fast simulators brought revolution in robotics around 2020, 2021, starting with Marcos Hutter lab in ETH. And now, of course, the techniques have improved and so on. And many consider robot locomotion to be a solved task. Okay, they can walk on any terrain. Humanoid robots also are excellent with very similar techniques and so on. So three ideas: super fast simulators. We train on augmented environment, not in one environment. You massively augment textures, terrains, and so on. And you train history-based policies that I don't want to go now into the details. These are very important for the robot to adapt at test time. So at test time, this is deployed without any training. Now for manipulation, the situation is much different. There again, robot teleoperation, is the dominant way, as I explained earlier. And this is for a good reason. As we said, when we want to train robots that walk around, we don't need to model how the terrain will react to their actions. But if you want to manipulate, the whole point of manipulation is the change that the robot actions are going to bring to the environment. So clearly, you need to model the environment, the objects, and the interactions. So this is much, much harder to do in simulation. But we say, what if we try? There are excellent algorithms out there. The graphics community has generated incredible algorithms that can simulate everything from plastic bags to bread to thin paper and so on. So these algorithms are out there. They're not all as fast as what I said, this walking on rigid terrain. They're not as fast, but they're available. And they would allow us to recreate the real world inside a physics engine if we would try. Yet, beyond the algorithms, somebody needs to make the bread. Somebody needs to make an asset. And so, unfortunately, you need artists for those assets. Recently, though, machine learning and generative modeling can help us bypass or complement those artists and really scale up asset generation in simulation. And in my lab, we are trying to build the whole pipeline automatically for generating robot data in simulation, from generating assets from images, from predicting their texture, arrange them in plausible configurations in the scene, defining tasks, define reward functions that the robot should optimize, and then get automated robot demonstrations without teleoperation. Okay? So let's see one by one the components of this pipeline, which we call generative simulation. So what about 3D assets? So in 2013, it was a year where Dream Fusion came out, the best paper award. It got the best paper award in ICLR. And it was the method that was able to map every 2D image to a 3D model by essentially solving this ambiguity of 2D to 3D lifting by rendering the 3D representation on novel viewpoints and evaluating the likelihood of that render with 2D diffusion models. So we'd use 2D generative models trained from images to generate 3D assets. So this was revolutionary. Now, since then, the community has generated, large data sets with millions of 3D assets. And, it has trained models that go from an image to a mesh, what you see here, automatically. With mesh diffusion models, which I'm going to discuss briefly. So the way those models work is as follows. They're latent diffusion models, which means that first you need to learn a latent space for your mesh. So you feed the mesh, you sample points on the surface of the mesh, then you subsample them. So you sample what we say, the surviving points are those point latents, okay, which you featurize, then you do lots of attentions, and you train the VA end-to-end to reconstruct back this mesh by predicting the surface normals at every XYZ location, predicting occupancy, and so on, and having also some KL regularizations. So you train that VAE, and the golden part that you keep is those point latents, which you then train a diffusion model on by adding noise and just predicting back the noise. And these latents is what you see there as the gray squares, okay? And this diffusion model takes an input image as the condition, and then iteratively denoises those point latents that can be decoded with the decoder of the VAE that I described earlier to a dense mesh. So what we've done in my lab is we saw that there's a limitation here. Every image is mapped to a single asset, but objects are compositional, they have parts. Scenes have objects. Can we jointly generate multiple assets at the same time? So we started from these massive latent diffusion models for mesh generation that I just described. These are 4 billion big models trained on millions of meshes. And we replicated those point latents. So instead of having one set of point latents, you have multiple ones. And then you jointly denoise them, essentially, and you generate multiple mesh. So the process looks like that. So this is an image, and jointly multiple mesh parts are generated, and the number of parts is a hyperparameter. You train the model under different numbers. And you can do this at object level as well as scene level. And you see the image has only 2 wheels, but the generated car has 4 wheels because the image is just a prompt into the 3D prior of the model. The model has been trained on complete 3D shapes. So a very partial image, even occluded image, would suffice to get the 3D asset out. So we're very excited about this direction. For me, this was inspiring because we always, the computer vision people are so obsessed with the image. Every pixel matters. But there are very few pixels here. So the big deal is not the image pixels that are used as a prompt during denoising, but rather the prior that you've trained, that essentially you're sampling from. So this gives you geometry, but geometry is not everything. You also need size and physics. And, you can ask a vision language model. Okay, what physics shall I put on my pumpkin? How big should it be? Because, there's no image, there's no size of the object in the image crop. And LLMs and VLMs have a good idea about pumpkin being larger than cauliflower, etc. And you can generate in this way assets for any object you want, any vegetable, any different cut of vegetables. So we've put a lot of effort because we care to make a simulator for cooking, actually. So we see this working well. Now you may say, how accurate are those physics? We don't care to make an accurate digital twin of the real world. We care to make a distribution of simulation environments, plausible ones, where to train the robot so that when a new real scene comes, this falls within the training distribution. Much like in locomotion, if you remember, where this robot was trained on was very, very different than where it was deployed. So this is about making scenes and making assets, etc. But beyond that, we need tasks. What should the robots be doing in simulation? And for that, we need to learn by imitating humans. Let's see what humans do. Let's see how they move objects around, right? So we really need to understand human activity to be able to imitate it within the simulation. So how can we understand human activity? So we are going to put effort on motion estimation. A video comes in, and we want to have very accurate motion estimates for every pixel. And up till 2022, many of you may know that the dominant approach in computer vision for estimating motion of a video frame was optical flow. Optical flow is a method that takes 2 frames and tells you for every pixel the displacement, the 2D displacement of that pixel. And the problem with optical flow, this pairwise essentially computation, is that pixels that get occluded, they don't have well-defined flow vectors. And this is a major problem. Each time there's an occlusion, you forget about the pixels. So when I interact with an object, there are very frequent occlusions, okay? So with Adam Harley here, my PhD student, we said we need to change the definition for motion estimation. What if we make the definition track any pixel in the video, also through occlusions? So we have this, point on the leg of a horse and want to track it through instantaneous occlusions throughout the whole video length. Okay, so this is very, very different than optical flow. So yeah, so how do we do that? First of all, we need to go beyond pairwise processing. We cannot be processing 2 frames. So we took a frame chunk, and the neural architecture that computes that motion, essentially that point trajectory, this operates in 1 point trajectory at a time, initializes the point trajectory assuming 0 motion, as you see here. So the nose goes in a very wrong place in the beginning, but then this trajectory feeds into a neural module and iteratively it is updated, okay? So you have this iterative computation that is actually extremely important and really helps performance. And it's okay if that point is occluded at some frames, even if some frames are missing. You just train the model to say if that pixel was, visible, where would that land, okay? So this is the architecture and this is the definition, and this is hard to supervise. Who's going to give you point trajectory ground truth through occlusions? This is impossible to annotate. So for that reason, we went to simulation. So here it is. We went to flying chairs and other very not realistic data sets, and we trained these point trajectory estimators, which we call PIPs, persistent independent particles, because it was one particle at a time that persists over time. And back when this work was introduced, everybody was really into computing motion and correspondence from real videos, and this sim to real approach, essentially, you just train in simulation and deploy on real videos, was able to do better than, methods that operate on real videos. And now you can, apply PIPs in every pixel and do dense point tracking. So recently we have extended this method to do prediction not of 2D pixel displacements, but rather of 3D pixel displacement to operate directly in 3D. And the motivation for that came from the fact that we realized that in videos, essentially, especially for videos of embodied agents like humans, most of the motion of the pixels is based on camera motion. So ego motion causes very, very large pixel displacements. So potentially, we could do better if we estimate those 3D point trajectories in an ego-stable space, where SLAM again comes, estimates camera poses, gives us depth, and then cancels that ego motion, and then you compute point trajectories on that ego-stable space. So we have a work in NeurIPS 25, we call it TAPIP 3D, that is very good when it takes RGBD sequences and generates 3D point trajectories, with or without camera motion, okay? And it exploits the fact that we have very good depth sensors, and we can, this iterative trajectory estimation I discussed can operate directly on 3D space. So what can we do now? We need to translate this in robot tasks. Well, actually, there is a very, very rich literature, and this is a very recent method that use actually TAPIP 3D to do that. So you take a video, it's a generated or real video, you track the points, and then you have a robot policy to imitate that 3D motion trajectory. And actually, we have our own method to be submitted soon that does exactly that. So you have a robot policy trained in simulation guided by imitating motion on a video sequence, okay? So you combine reinforcement learning with imitation learning. And point trajectories, what we propose is now a very, very important concept for capturing robot sub-goals, grounding robot sub-goals. Of course, I can describe a robot sub-goal in text, close the laptop, but the grounding of that text is actually, the point trajectory is going to go down, right? So it's a grounding not on video pixels, not on the video, but rather on the motion of those persistent entities. So it's a more physics-aware representation. So as I said, we are in simulation, and we train a lot of robots picking up objects, lots of different assets, thousands of different assets, leaving them down, moving them around, pushing them to different locations. So essentially, you do this idea of large-scale RL, much like in locomotion, and then we essentially guide those skills based on these point tracks that I just showed you. And another thing we do is we can chain those skills over time using a tree search process guided from VLMs that suggest what skill to do and check at every step of the process whether the correct sub-goal, whether the proposed sub-goal has been achieved, okay? So you have a longer task of putting objects inside the drawer, and you need to open the drawer, pick it up, move it inside, and it's very hard to do RL for the complete task. We do reinforcement learning for the skills, and tree search is essentially link those skills over time. And we hope in this way to create this, what we're working on, a data flywheel of continual robot data generation in simulation to train our VLAs, as opposed to training from demonstrations. Another big problem that we think simulation may help us is on benchmarking. So with VLAs, etc., papers keep coming out, and very good results are on Twitter, but nobody knows how well these methods actually perform, because actually there's no benchmark that can take a VLA trained on any data and then test its capabilities. So we think that simulation holds also this premise of large-scale evaluation, scalable evaluation of VLAs. So if you know how robot policy evaluation works, is you have your robot, you set the scene, then you run the robot policy, you see the result, you need to decide whether your robot succeeded or not. So clearly there's a bias of whether your model or the baseline runs on the robot, and then you reset the scene and you do this again and again and again. So it may take an engineer multiple hours to figure out if the new VLA version is better than the old one. So this problem of evaluating foundation models is not new in robotics. The same problem is for language models. How can you tell when one LLM is better than the other? There is a very beautiful framework here, Language Model Arena, that originated from Berkeley. For Language Model Arena, if you go online, you'll find a website where each one of us can submit a task, like what you see there, the user is asking, and then two anonymous LLMs will be sampled to answer the task. So you don't know what LLM is each one. And what you do is you cast a preference, which answer you like best. And then these preferences are aggregated across dozens of thousands of users, and then the leaderboard is generated. And as LLMs go up and down in the leaderboard, the stock market is affected, because it's very important that once company's LLM or VLM dominates the other company's model, okay? So we have a leaderboard that we can trust for LLMs. At least many people trust. Can we do an analogous thing for robots, where a user can come in an interface and submit a task and say, okay, here's my kitchen, even take a picture, make a robot to arrange the plates on my kitchen correctly, ready for dinner. That's what we envision. And the only way to do that is in simulation, okay? So we have done a first step in that way by generating a lot of simulation environments automatically from real-world videos. So we take videos, and it can be a robot doing something or a human doing something, and we make the corresponding environment in simulation and the corresponding task instruction. And we've done this by taking videos from different data sets. Our end goal is the user to give us an image, and we'll take this image to a 3D scene with different objects, as you see. So this, everything you see here is the simulation environments with background and the different objects and physics and so on. And now, based on the task instruction, we're going to deploy VLAs in simulation. And the ones we picked is COGACT, RoboVLM, Special VLA, and Octo. And since then, we have thrown many more. One limitation of the previous benchmark that I showed is that the background here is just flat, so the camera cannot move. But using generative models right now, we're working on taking the background image into a complete 3D scene. So the robot can move in there, and you can put wrist cameras on the robot, and you can view any viewpoint. So then we'll deploy those VLAs in simulation, and we'll get the execution videos, some of which will be successful, some will not be successful. And then what we're going to do is we're going to show them to human users. And of course, we also have an automated scoring mechanism, because it is easy to tell, if the robot succeeded or not using either VLMs or using privileged information from the simulation. But as robot policies become more and more competent, we think that humans should cast preferences, say, I like this robot, it was faster, or it was smoother, or it went around, my table the right way. So we did that, and we aggregated thousands of human preferences, and we made a leaderboard. And we see here that COGACT and RoboVLM are much higher than Octo and Special VLA across hundreds of environments, and also across a lot of variations of those environments. Because we're in simulation, we can vary where the objects are, we can vary the texture of the background, vary the camera viewpoint, not yet, now we do it only in our 3D version, but change essentially in the environment and stress test the generalization of those policies. So as we invest in simulation, the physics engine itself is a big question. This is Yan Zhu, who is a PhD student of my group, who graduated last year, and him and his team have introduced the Genesis simulator. It was released a little bit more than a year ago. It is open source. So what the Genesis physics engine is essentially a physics engine like the others, but it has codes up many different physics solvers in the same place, all in TaiChi. TaiChi is a GPU parallelizable programming language that came out in 2018. It can handle diverse materials, rigid, articulated, liquid, gas, deformable, thin shell objects, granular objects. This is very important for a benchmark, as we're trying to extend it beyond rigid or piecewise rigid objects with the cups that have water and so on and so forth, and cloths and towels and so on. So the performance is very good for piecewise rigid scenes. And of course, the simulation of deformable materials is slower, but still twice as fast as any other previous physics engine. It has also very good renderings that look realistic. So I would say the visual fidelity of physics engines is excellent, right? So we know that Hollywood have closed the sim to real gap, right? We watch movies, we don't know if it's real or it's generated. So this is not a problem. And here the physics solvers can take care of different parts of the scene. You can have rigid with water, or rigid with deformable, and so on, and thin shell objects, etc. And here is the strawberry with the water. So we have a physics engine that actually can simulate a lot of different materials. Now I'm, of course, a big, fan of this physics engine, but at the same time, we do have an active project of trying to train neural nets, much like physics engines, with points being every little token to be a point trajectory, and train them from the results of those engines, so that eventually we can, throw physics engines away and only have neural networks predicting this 3D generation. Okay, much like a physics engine, you can feed them physics, you can feed them physics properties and so on, and do similar results. The reason for that is that the downside, and of course I'm not going to show any visuals of that, is that if your mesh has a problem, then the simulation is going to explode, the physics solver is not going to converge, and you may see your object flying. So you want to use good simulated data to distill them into 3D point trajectory generative models, so that eventually we can throw away the physics engines themselves. So the last part of the talk is about planning with generative models. So planning is extremely important for the following reasons. It is a reality that robots and machines that test time think do better. And here is the game of Go, okay, with a mu0, actually with a learned simulator of the game, that as you sample at test time more simulations in your Monte Carlo research, you do better, right? So Monte Carlo research is used both at training time, and it's terribly important to be used at training time to discover actions faster than just model free RL, but it's also used at test time. And this test time planning is extremely important in strategic games like Go and in chess. Now, if you go to bullet chess, you don't need to test time think. You can actually emulate human decisions. You can do better than humans without any test time thinking. Because these are easy decisions. But once you go to chess that you allow humans to think as much as they need, like you have much longer duration, 3 hours as opposed to 10 minutes, then the machines need to test time think. One question would be, why we need this test time search? Why don't we just have a big model, right? Can't model capacity be large enough and trained in simulation with lots of data? And there's no need on Monte Carlo research. And this is actually true. For many games, like Atari, you don't need to do test time search. If you generate a lot of training data, you can directly play reactively at test time. And indeed, you don't have much time to think because the Atari simulations just keep running. Now, this paper is absolutely remarkable, scaling laws with board games, because it shows that you can trade off model capacity with test time compute. So you can have a smaller model where you spend more time planning at test time, and it's going to do as well as having a bigger model with less test time thinking. And, people have shown that if you want to get rid completely of test time thinking, it's actually very, very difficult. You need immense amount of resources. So test time thinking is actually a very powerful mechanism when you are OOD or when you're in a difficult situation to do well. So what is this test time thinking for robotics? For robotics, it hasn't really worked yet. We don't see robots that don't fail, right? So we humans never fail. We just spend more time. So you go to drive, you do your commute, right? Your daily commute, very easy. You Zoom, you talk to your students and friends while you're driving. Then you have a difficult drive on a new neighborhood. It's dark, it's raining. You are very focused. You never say, I failed to drive, okay? But robots just fail, right? They cannot spend time thinking and do better. So this is the premise of those world simulators, that with more thinking, they'll do better. So what is the traditional model-based control? Okay, so you have a data set of state and actions, and then you also have a reward function. And what you do is first you learn a predictive model, a next state function, essentially. And then you do optimization over actions. And this really doesn't work very well for multiple reasons. First, because the next state function is never deterministic the way you trained it. And second, this action optimization that you're searching over actions to maximize your rewards of future states is going to exploit any mistake on your model, okay? And the question is, generative models can now generate these fantastic images and videos of yourself doing, stand-up comedy, crazy things. Can they help us in this problem? Why model-based robot control is so hard? And what if we revisit this problem in a very different vein? What if instead of next state function, we train a generative model over robot trajectories, state trajectories or state and action trajectories directly, not one time step at a time. And also the generative model will capture multimodality. That is not going to be deterministic. And then at test time, when you have a specific reward function that needs to be differentiable, you can guide the denoising process. In diffusion model, you go from noise to signal. So each time you denoise, okay, you predict the clean signal x0 given k at every noise level k. You can adapt that x0 by taking a gradient with respect to your reward function. Okay, and this is called the guided denoising, guided diffusion. And it is actually extremely powerful. So I'll show you here. Here we have some humanoid robots where you train a diffusion model over humanoid state trajectories. And now you want to give it a new task. For example, you ask it to follow the yellow points. You're going to see some yellow points. And you don't tell it anything else. You don't tell it how the body should be arrange to follow those yellow points with your wrists. You just let guided diffusion to do the thing, and you see that, the humanoid is going to lean forward, is going to bend automatically without you commanding it to do so and without your reward function telling you to do so. And the reason this happens is because your generative model has captured the manifold of motions of your robot. So it's going to search in this manifold to optimize your reward function. So you have captured the priors of how robots move and how they manipulate. So we really try a lot of, like this data generation in simulation that I showed you, we distill this data into diffusion models, which we guide to do different things, to pick up the objects from different ways, to move the fingers in particular ways as we watch videos and the tracking that I showed you earlier. So we do this essentially guided denoising. Now, the reward function that I said needs to be differentiable, but what if it's not differentiable? And in autonomous driving, if you want to do the same thing, test time planning for autonomous driving that we mentioned earlier, the reward function has a term that is not actually differentiable. Trackability. How trackable? How well can your controller follow a specific trajectory? So here's what we're going to do. We're not going to do this guided denoising with these equations that I showed you earlier, but we're going to do something much simpler. The first thing is the same. We're going to take trajectories from a vehicle and fit a generative model on them, okay? And now, when we do this action optimization, for example, the simplest thing, evolutionary search, we're going to inject information from that generative model in a very intuitive way. So first, we're going to sample some trajectories. So this is when we have the population, what we call the population evolutionary search. Then we're going to score those trajectories, and indeed the reward and cost doesn't need to be differentiable. And next, what we're going to do next is now the important thing, is this mutation. So mutation in evolutionary search is you take your sample and you add noise to it. So once you have a beautiful trajectory and you add noise to it, you destroy the trajectory. Probably it's going to be some super weird trajectory, right? Imagine you have a robot trajectory and you add noise, something really ugly is going to come out. But now we have a generative model. So instead of just adding noise and getting some crazy trajectories, we can also do a denoising back to push those trajectories back in the data manifold. So the mutation process now is a learned process, okay? And you can mutate a lot. So it depends on how much noise you do. You have an initial trajectory at 0, and you can add different amounts of noise, and you can denoise, and now you have these mutations that are all valid trajectories, okay? So you're not going to jump a lot outside your data manifold. And so now you have this, and this lands in a better optimization process, which we call diffusion ES. So it's evolutionary search with diffusion during this mutation process. And here I'm showing all those steps. So what can we do now with this better, let's say, evolutionary search, this better MPC for driving? We can talk to our car. So we can generate driving data. You know that the same with robots. For driving, the situation with the data is a bit easier because, it's very easy to record the data. And in fact, if you buy a Tesla, I think you sign something that all your driving data are going to be sent to the company. So it's easy to collect the data. But, if you see all the academic benchmarks, 95% is just driving forward. So you cannot learn a lot from driving forward. You want to see interesting things, bypassing, turning left, and, parking on the side of the road, and so on. So now with this optimizer that I just described and some reward functions, which we're going to derive from language, we'll be able to generate this data ourselves, okay? Much like in the simulator that we're generating our data. So we'll start from some interesting behavior in language. Car 3 will slow for you, change to the right lane now, and we'll feed that into a language model to spit out a Python program of reward functions. And this language model has some prompt just to guide it a little bit. And essentially, what the program is going to do is going to tell you which lane to go and which center point to go close and which, part of the scene to avoid and so on. And then we're going to take these reward functions that are pretty complex and we're going to feed them to our evolutionary search. And it's only diffusion, yes, that manages to optimize them correctly. Without diffusion, plain evolutionary search or MPPI and so on, MPI that people use do not manage to optimize those well, okay? And in fact, we compared here with a lot of alternatives. So I'm very, very excited about what generative models can bring in this robot planning domain. So 3 things that I discussed, and this is the takeaways from my talk. The first is inductive biases. This is a little bit scary because we know the bitter lesson that says no inductive biases. You just need to do data and search. But somehow, me coming from 3D computer vision, I'm still very attached to these things, and they seem to work. But then we discussed about how to scale up the data and how generative modeling computer vision can help us, and then how we can do better search with generative models. So with this, I want to thank the students and that worked on this and our funding agencies and you for your attention. Thank you very much.
Thank you very much, Katerina, for an amazing talk. I'm just going to admit that there are very few people that make me so envious about how much great work they do and how amazing their presentations are. I need to go back to the lab and work harder to make my own work better. But so thank you very much for that amazing talk. Please, if you have any questions, come up to the microphone and just give your name and affiliation before you ask your question. Wait, microphone? Yep.
Hi, I'm Pradeep. I'm a faculty from the Singapore Management University. Very interesting talk. One of the things we have been doing is trying to use diffusion models to replicate trajectories. If you give trajectories, can we generate trajectories which look similar to those trajectories? And one thing we constantly find is that there's a lot of error in the dynamics. And in the last work and also in the vision works, I didn't see any results on how much of the dynamics are accurately being represented and how much error do you see in the dynamics. Do you have any thoughts on that? And that's the main question I had on whether diffusion models are good for representing trajectory dynamics.
Yes, thank you for your question. So in the driving part, we did use diffusion models to generate whole trajectories of the vehicle. And they were extremely accurate. In fact, we were at the top of the benchmark of new plan, and we also did very well with driving. We actually track these trajectories with PID controllers and go to the right place. Now, not only we use this is a little bit earlier work, but in the VLA that I discussed, we use diffusion to predict trajectories for the robot grippers. And again, they're at the top of the 3DFA work, 3D flow matching work. It's at the top of the bimanual manipulation benchmark, so clearly it's doing really well. And not only that, but right now we're using, as I didn't show results, but we're using diffusion models for point trajectories of the whole scene in a physics engine with different objects colliding on top of each other and so on. So I think they're absolutely extremely accurate. And there is no reason not to be. Why would they be so accurate on generating images that are also extremely complex, the data manifold, and videos? The dynamics in videos are very complex. So point trajectory is just a form of dynamics as well. And yes, we haven't, we didn't have any problem, yes.
Yeah, so we were using Mujoku domains, and there when we gave trajectories and when we asked it to generate trajectories, somehow there was a lot of error. And maybe the type of diffusion models you are using are different here, or is it specific to images? And
yeah, this is a great question. So for Mujoku domains, so just to be clear, all VLAs right now, most VLAs, like 90%, they do use diffusion heads and they spit out join angles. Now, the truth is that state diffusion is much better than action diffusion. And in fact, so there is this a little bit of a tension. Should I be denoising state and actions together, or should I just be denoising states, essentially, where should as opposed to PD targets? And we don't use diffusion models to denoise PD targets. We tried that and it didn't work. We always use diffusion models to denoise states of the robot, like 3D end effectors. Also for the humanoid, I need to tell you that we try to denoise join angles, not PD target, join angles, and denoising in the 3D representation, 3D key points and 3D rotations of the angles worked much better. So I think also maybe potentially the representation where you use matters. For the vehicle, again, these are waypoints, very simple, very easy to fit. For Mujoku now, I'm not sure exactly if you're talking about PD targets, we're talking about joint angles, we're talking about 3D representations. I think the details here matter a lot. But I'm happy to discuss this offline more.
Yeah. Thank you, Katerina. Excellent talk. Really enjoy. My name is Juan Vax from Purdue University. I wanted to know your thoughts about basically getting rid of simulation altogether. So basically training as you test, the way that we do when we try to do something new or even, experiment in the world. We don't really run a simulation, right? Or we simulate in some way, but we're able to interact and learn as we do the task, right?
Yeah, excellent question. So I think what you're saying is we don't set up a physics engine with particles and Newton laws. We are very intuitive on the way we simulate the future, what would happen, and so on. Yes, so the answer is as follows. There are people that try to get rid of physics engines by doing video generative models. And this is, a competitor. And they're doing really well. They're very wasteful. But, this is one thing. I'm not sure if we imagine things on the observation space, that we imagine like surfaces of things as opposed to 3D. Another thing we are trying is intuitive 3D generative models. What if we predict trajectories in 3D? Okay, this is what I told you. Copy-paste what the physics engine do, but with a neural network. However, I also think that this is incorrect. There is a paper that says humans form abstractions when they plan. So you don't plan the exact trajectory, you just predict. Now you're thinking how you're going to get out of the auditorium, you just predict, I'm going to go there, I'm going to go there. You don't need to generate the exact particles of how your hands are going to move, okay? So I think these abstractions matter a lot, and part of that world models that we build in the head, I think for sure text or some abstraction like, okay, go there, so we can simulate only what is necessary should be present. But regarding physics engines, I do believe that in a few years from now, maybe 5-10 years, we're not going to have physics engines. Yes, we're all going to be neural.
Thank you. We'll go to the middle here, and then our final question over here.
Okay, this is Xiang from Huazhong University of Science and Technology in China. Very impressive and systematic work, but still there's seem to real gap, right?
Yes.
So then how can we ensure the model, for example, VLM model trained using this kind of data is safe and reliable after employment?
Yeah, this is an excellent question. So this question has multiple answers. First, we are trying things that the locomotion people do. We don't train in one version of reality, but we take, let's say, the cell phone, we augment the textures, we augment this, how slippery it is, we augment the mass, and then we train history-based policies to manipulate it. And this policies, essentially, the history of proprioception is a very powerful sensor to tell you in what version of reality you are from what you simulated. So you don't train in one, you train a distribution of simulation scenarios, okay? So that's number one. Number two, we see this as large-scale pre-training. I think that RL in the real world is the absolute AI challenge. That's what humans do. They're so efficient. And I think pre-training in simulation and doing reasoning correctly at test time so that you don't knock out all the objects when you're planning your trajectories and each time you make a mistake is extremely important. So the reasoning and test time thinking when you are OOD, it's extremely important. Yeah, it's just I'm not sure I have another alternative due to the scarcity of demonstrations I have access to.
Okay, thank you. I'll talk to you later. Okay.
Hi, my name is Silvia Tulli. I'm from Sorbonne University in France. And I wanted to ask how much what we learn is dependent on the specific embodiment that we have, and if what we are learning in a specific embodiment can be translated to other embodiments, and how much this translation happen. Because I have the impression that oftentimes we learn for that specific type of robot. And I wonder if, for example, one step towards filling the gap sim to real could be to have even like simpler robots in which we start to test the algorithm and then go to other type of embodiment. But the question here is how much there is transfer between what I observe in a simpler context to a more complex embodiment.
Yeah, excellent question. So one answer there is the following. Human babies, when they go from crawling to standing, they say they relearn everything. The viewpoint is so dramatically different. So there is some embodiment specific here idea. And in fact, I think the embodiment learning, it's all about embodiment. And this fantastic locomotion, the results that you saw, they are fantastic because they look at the history of their proprioceptions. They managed to essentially, what were the prior states of the legs and what were the PD targets, the actions you commanded, and they can translate those histories into what I should do in the future. So in the low-level mobility, I think embodiment specific is terribly important. Yeah, and that's the whole point of intelligence and physical in embodiment specific intelligence. There is a part of the world, like how objects move. If I throw this, it's gonna break, and how the world changes, how the objects move and how they operate, and how that the laptops open and close, and they have a button that you can open and close them. This is embodiment agnostic. So there is a part about the world, and there's a part about low-level actions that you want to do. So sub-goals in the form of where objects need to go and key points of those objects need to go potentially can be widely shared across robot embodiments. Yeah.
Okay, thanks.
Thank you.
So I will say I have many questions myself because that was such an amazing talk. But we would like to thank our speaker one more time, and you can ask questions offline right here just after the session. Thank you so much one more time.
Thank you.